Okay, so hope all of you had a good break, and let's get back, and we will have to sort of pick up speed a little bit now. But anyway, I think we have covered a lot of ground, and it's more about putting things together now. And I hope to start discussing quantum algorithms well and truly today, right? I want to mention that I will post the next assignment, which is assignment 3 today, okay? And it will be due exactly 10 days, right? If I post it today, then it will be due 31st. If I post it tomorrow, it will be due 1st of November. And I will not grant any extensions this time because there's also going to be an assignment 4, all right? And this assignment, which is assignment 3, will have two components. There'll be one part which will be problems like I always give, and those will have to do with quantum gates basically and circuits. There will be a part where you will have to implement certain tasks on IBM Q. Okay. And I should mention that all of you now have access to the IIT IBM classroom. Okay. So all of you now have access to under the IIT IBM, I don't know what it's called. I think it's called a classroom. But if you log into, so the key is to log in to IBM using your Smail account. Okay. So use your Smail, which is essentially a Gmail, right? So use your Smail account. Okay. And log into IBM, and then you will have the option of joining the IIT IBM class. What this does is it allows you to run tasks without having to wait too much, and it gives you access to many more machines. Okay, so please do this and let me know if you're able to access. If you have any queries, you can also contact your TAs. I will upload these instructions on Moodle as well. Okay, so this will be your assignment 3. Okay, where you will have to do a couple of tasks at least on IBM processors, so that you have some hands-on experience working with a real quantum processor. Okay. All right. So let me quickly recap now. I had to make a few concluding remarks on universality, which I didn't have time to do last time. Okay. Just check. Okay. Yeah. So the first is, of course, let's recall that there could be two sets of gates I mentioned, which are universal quantum gates, right? And then, so this is the Hadamard, the phase gate, and the T gate, which is the pi over 4 or the pi over 8 gate, right? And the C naught. Now, in this, note that the C naught, as you know, is a 2-qubit gate, right? And then you have the Toffoli, which is a 3-qubit gate. And as I mentioned, this is the controlled knot, right? So it flips the third qubit, the target qubit, only if both controls are set to 1, right? And an alternate set could be that you implement a 3-qubit gate and then you have only the Hadamard single qubit gate to implement. Now, whatever I have been discussing as a so-called proof of this universality has to do with the first part, right? So this is the part that I'm discussing, and I said this universality is itself a two-step process, right? So showing universality of this set is a two-step process. So the first step is to show that any unitary which could be D cross D in general can be decomposed as a product of single qubit unitaries and C naughts. Okay, so this statement, I have only proven one half of this, right? So the last time, so recall again that we showed last time that any element of SUD, that is, or you can just think of this as UD, doesn't matter, which is basically any D cross D unitary matrix can be written as a product of, actually, let me not say this way, let me say that can be realized as a sequence of, so that I make it a circuit statement. So it can be realized as a sequence of this, okay? And let me say the product statement here, that any D cross D can be written as a product of what are called two-level unitaries, right? I know it's been so long ago, but I hope you recall this. And what we showed was that you could have, so we did the 3 by 3 example, right? Where we showed that if you have, so the idea is that any such U can be written as some U1 dagger, U2 dagger, etc., UK dagger, where all the UIs are of the form. So one example could be like this, that they have only these entries populated, right? And they are identity, all the other diagonals are identity. Remember, I also made this error last time. So all the diagonals have to be identity, right? And all the other entries are zero. All the other off diagonals are zero. And you have two diagonal entries and two non-diagonal entries, exactly. And these off diagonal entries obviously have to sit in somewhat complementary positions so that this forms a unitary. So this is what we call a two-level unitary, right? I hope this statement is clear, that any D cross D can be decomposed, and we worked out the example of a 3 cross 3 unitary, and we showed how you can do a simple algorithmic procedure by which you can decompose it, and this required how many two-level unitaries? So this required 3 such two-level unitaries, and in general we said a D cross D would require D into D minus 1 by 2 unitaries, right? Okay, so now the second part of the statement is that such a two-level, so once I have an arbitrary unitary as a product of these kind of two-level unitaries, we said the two-level unitary acts non-trivially only on two states, right? On the rest of the state, it acts trivially, meaning like identity, right? So this acts non-trivially only on two states of the whatever is that dimension, right? So maybe D is 2 to the n, in which case it's an n qubit system, right? So it acts non-trivially only on two states, right? Two orthogonal states, and acts trivially, which means like identity, on the rest of the basis. So let me say only on two states of the computational basis. Okay, so that is what a two-level unitary is. Now I'm just going to show you a simple circuit, okay, as to how a two-level unitary can be implemented. So the next part of this statement, so if I call this as 1A, right? This is 1A. Then I have a 1B, which is that any two-level unitary can be implemented using C-naughts and single qubit unitaries. So let's do again, let's show this by an example. Imagine I have this, imagine I have this 3 qubit unitary. Okay, imagine I have this 8 cross 8 unitary. So this is acting on a 3 qubit system, right? And imagine that this has this form, right? That it is A, B, right? and then everywhere else is zeros. Okay. So, sorry, this is, sorry, I wanted this to be B and this to be C and D, right? Okay.
Excuse me, ma'am.
Yeah.
Just wanted to confirm something.
Mhm.
So the form that you're mentioning, this two-level unitary, this is not the only possible form, right?
No, no, it's not. It's not. Indeed, it's not. I was thinking when I made that statement that people should not. So this is an example of, let me say it's an example of the kind of form. Like I said, it can be, I mean, we looked at different examples, right? So you could have A, B, C, D, oops. Okay. And then the rest are ones and then zeros, right? This is one possible form, correct? And there are several such forms. You just have to pick, like I said, complementary of diagonal entries. And then, yeah. Is it clear?
Yeah, sure.
Okay. So, I mean, this is just a form I've picked for convenience. So now, if I look at this in the computational basis of the 3-qubit system, there are only two states on which this is acting non-trivially. That's what we said, right? So if you look at this from the computational basis point of view, then you have kept 1, 0, 0, I mean, sorry, 0, 0, 0 sitting here, 0, 0, 1, etc., all the way up to 1, 1, 1, right? Similarly, here I can write this as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, not having enough space, 1, 1, 0, and 1, 1, 1, right? Is it clear what I'm doing? I'm just writing down what are the basis vectors corresponding to the different locations, right? Is this clear? So now, which are the two states on which, so these matrix entries correspond to these states, right? You're writing it in this basis, right? So which are the two states on which this unitary is acting non-trivially? Can you tell me?
First and eighth.
Correct. So that is basically the 0, 0, 0 and the 1, 1, 1. So this unitary is acting non-trivially only on 0, 0, 0 and 1, 1, 1. And if I were to think of 0, 0, 0 as a different 0 tilde and 1, 1, 1 as a different 1 tilde, then on this 0 tilde 1 tilde, it's essentially a single qubit unitary U tilde of the form ABCD. Is that clear? So if I were to say that 0, 0, 0 is something called 0 tilde and 1, 1, 1 is something called 1 tilde. So in the language of error correction, these would be called logical qubits. It's a logical 0 and a logical 1. It's not an actual 0 qubit. It's like a logical 0 level and a logical 1, right? It's on a two-dimensional subspace of this larger space. So then there is a U tilde, which is ABCD, and essentially it acts on 0 in this basis as this kind of a single qubit gate, right? So this is a single qubit gate on 0 tilde and 1 tilde. Is this idea clear? Okay, so how does this help us? Well, basically, we are now going to show that such an 3-qubit unitary can be implemented using this single qubit gate, right? And a bunch of C-naughts, right? And I'm just going to draw the circuit for you, and then I will leave it to you to basically judge whether it is correct or not. So I'm going to write down now 3 indices like this, X, Y, Z. It's a 3-qubit circuit, right? So basically it has a bunch of X gates, okay? And the X gates are there to get the correct condition for the C naughts, okay? So I'm drawing actually here a double controlled C naught, but that's a separate statement that the double controlled C naught can be implemented using single controlled C naughts and Hadamard and so on, okay? That's a separate argument, but just assume that that is the case for now, but I just want to show you that So the second part simply reverses whatever is done in the first part by and large. Okay. So you see the heart of the matter is here, that you have a double controlled U tilde, right? The point is U tilde has to kick in when either when all the three qubits are 0 or when all the three are 1. Correct? So all the other controls are essentially to get that conditioning, right? So this has to be active when the inputs are 0, 0, 0 and 1, 1, 1, right? In all other cases, this double control should not kick in, right? So the controls should be active, or the controls are on when the inputs are either 0, 0, 0 or 1, 1, 1. And in all other cases, the controls should be 0. I mean, basically, yeah. So in all other cases, the controls don't kick in. If the controls don't kick in, then nothing happens. That's what a controlled unitary gate does. It applies the unitary only when both the controls are set to 1. So you have to make sure that both the controls are set to 1 only when these two states are the inputs, and otherwise both the controls should always be off, right? Okay, I hope you can still see my screen. Yeah. So this is basically the circuit that achieves this. So the 3-qubit unitary, which was a 2-level unitary, can be achieved like this. So you see, this entire circuit is just to implement this arbitrary 3-qubit unitary. Okay. So this is a kind of, art and science in itself, right? How do you take an arbitrary unitary and break it down into the sets that you have, right? And so this seems to be the most elegant matrix algebra approach, that you first consider any arbitrary unitary as a sequence of 2-level unitaries like this. And once you have these 2-level unitaries, it's just a matter of identifying the right sequence of controls so that that 2-level unitary can be replaced by a single unit, so you need to have the ability to have these single qubit gates, which is all the X's. You need to have the ability to do these controls and this U tilde. Okay. Now I'm not going to sit and analyze this circuit. That will take me the rest of the hour. Okay. But I leave it to you to sit and analyze this circuit carefully. It's a good exercise. Okay. So your exercise is to check this, right? To check that the controls are on only when the inputs are 0, 0, 0 and 1, 1, 1. Okay. So please check this, but this is just a demonstration or an example to show that this is what is achieved. This is how you can achieve an exact universality statement. So the first statement, what we just argued, is what is called an exact universality statement. Okay. Because any unitary, any D cross D unitary can be exactly decomposed as a product of 2-level unitaries. Any product, any 2-level unitary can be exactly implemented using C-naughts and single qubit unitaries. Okay. The second part is going to be an approximate statement, because now what have you done? You've gone from arbitrary D cross D unitaries, which is arbitrary quantum gates, to single qubit unitaries and C-naughts. Now the last part is to show that the single qubit unitaries can be themselves realized using only a small finite set of gates, right? And that finite set is basically Hadamard, S and T. Okay. So while this is an exact statement, this can only be an approximate statement. Okay, because the set of single qubit unitaries is a continuous parameter group, and to be able to realize a continuous parameter group in terms of just some discrete finite set obviously cannot be an exact statement, right? So this is the second part of the universality argument, which I will just state now, but again I'm not going to get into the proof of it. It's a somewhat involved proof. I will put this in the assignment as a kind of extra exercise for those of you out there who are, I don't know, who are like Hermione, who like to do extra work for class. You can just take a look at the second part of the assignment where I will outline what the argument is. It's a fun exercise to do if you like playing around with matrix algebras, right? Okay, so this is the first part and this is the second part. So the second statement I will just state here. Was there a question?
Yes, ma'am.
Yeah.
So that means that the C0 decomposition is not like it's not finite necessarily, right?
Which C0 decomposition? I didn't
Like the
understand.
C0 unitary decomposition of the two level thing is not finite in length.
Which one? This one?
Yeah,
What
the first statement, the exact statement.
Well, it is finite, no? Because you need only d times d minus 1. And then each of these will require a certain number of single qubit unitaries and C0s. The point is, it requires you to have the ability to do arbitrary single qubit unitaries. See, I must now be able to do some arbitrary ABCD like this. Now, no physical architecture is going to have the ability to do arbitrary. You have like, essentially 4 complex parameters. You can reduce it to 3, maybe, right? So if you have the ability to do arbitrary single qubit unitaries, then you're done. You don't need the approximate statement. The approximate statement is only to say, if you want to do any element of SU2 using some discrete set of gates.
Oh, okay.
The approximate. You understand?
Right.
Yeah. See, it is not that the circuit depth will blow up or something. It is more that for every arbitrary D cross D unitary, I will have arbitrary elements of SU2. And so my architecture then must have the ability to do arbitrary elements of SU2.
Right.
Okay. So
Yeah.
indeed you have such an architecture. For example, one approach to doing that would be to decompose any element of SU2 in terms of rotation gates. Then if you
I
have
was
the ability to do
actually
arbitrary rotations, exactly,
right.
yeah. So you could then again reach very close to exact universality. But this statement was more from a computational theory point of view, that does this quantum computing idea even admit such a discrete finite set? Right? And the answer is yes, it does admit such a finite set, which means you don't have to tweak anything, right? You just build up your circuit using these blocks. It's like saying that I have exactly 4 blocks. I have a H block, S block, P block, and a C0 block. And I just keep putting them together and I get any arbitrary unit. That is where the approximation angle comes in.
Right.
The idea clear?
Yeah, it's clear now.
Yeah. So I think it's true that today, for example, on IBM, you have the ability to do rotation gates and you have the ability to do arbitrarily close rotation gates. But the point is, if you end up with some kind of irrational angles there, then obviously it cannot be an exact statement. So in fact, in this approximate statement, you will find that you hit such a roadblock. Okay. So I will outline this approximate argument in the assignment, right? And then you'll have to use some kind of pigeonhole argument, right? To say that you can get arbitrarily close to, it does rely on rotation angles. The approximate result also finally relies on some kind of rotations. But the angles, you have to get arbitrarily close to, all kinds of angles, right? It's a continuous interval from 0 to pi or 0 to 2 pi. So the ability to do that using some discrete gates, that's where the approximation will finally come. But I want to now talk about what do I mean by approximate. Okay, like I said, even with the exact statement, it's possible that I end up with some random angle if I have to break it down in terms of rotation unitaries. how close can I get to such an angle, right? But then in the gate sense, what does it mean to say I'm approximating a particular unitary? So that's what I want to talk about now. So the second statement, like I've been saying, is an approximate universality statement. So the question is, how do you quantify this approximate part? Okay. So I just want to briefly talk about that. So this is a question of quantifying the error, right? So now, suppose we need to implement a gate. We need to implement U, but we instead implement V. Okay. Now, how do I argue that V is somehow very close to U, right? So one way to argue this is using the action on states, because that is the operational part finally, right? I really don't care about how close two matrices are in some abstract sense. I care about their action on states, right? So then let's say that the error is what I call E of U comma V. It's some function, right? I call this an error function, okay, E of U comma V. And I say that E of U comma V is basically the difference between the two states, U acting on a particular state psi minus V acting on a particular state psi. Now, obviously, this is not a very well-defined quantity, so I have to take the modulus of this. But more than the modulus, actually, I have to take the norm of this, because this difference is also a state, right? This is some other vector, right? And this is for a particular state, with reference to a particular state. So I have to really maximize this over all states. So what does this definition mean? So I will write this more succinctly actually as max over psi, U minus V acting on psi, the norm of that. Okay. So this in words, in English, what this means is this is the norm. This is the maximum norm of the difference between the action of U and, right? So basically you take the norm of the difference between the action of U and V on a particular psi, and then you maximize this over all psi in your space, right? And this really will capture what is the error, right? You have to, so this is what we would think of as a worst case error, right? Because there will be some states on which this difference may not be much. There may be other states on which this difference can be very large. And if you want to say that this is how close U is to V, then you must take into account the worst case difference caused by implementing V instead of U, right? So I hope the definition is clear. So this is just the norm. The two parallel lines are just the norm, right? And in another couple of minutes, I just want to show you that this is a very operationally sensible definition, because it then tells you how the statistics differ, right? What happens if you implement V instead of U is that the action, of course, will change. V acting on psi will be different from U acting on psi. But finally, when I measure these two states, their statistics will be different. And as you will see in any quantum algorithm, it's the final measurement statistics that matter, right? So operationally, this error should quantify the error in the measurement statistics, right? So the statement will be that if this error function is small, right, then any measurement on V psi will give approximately the same statistics as a measurement on U psi. Okay, so this is what I just want to argue to make sense of this error function. And the way you can do that is actually by using POVMs, right? So you can essentially then show that, so let me just leave this statement here and actually not prove it. Again, that's going to take me another 5-10 minutes. I would rather move on to algorithms now. So let me just state this clearly. So let Mi be an element of a POVM. So I hope everyone remembers what POVMs are. So there is a measurement M with associated positive operators Mi, right? Then you say that Pu of I is the probability of outcome I if the state is U psi. And then I want to say Pv of I is the probability of the outcome I if the state was V psi. And now I want to argue that this error function actually provides a bound on the difference between these two probabilities. If V were the same as U, these two probabilities should be the same. But V is different from U, and how different V is from U will tell you how different these two probabilities are. So that will tell you how different the statistics of the outcomes will be, right? So the statement is that modulus of the difference of these probabilities, right? This is simply the modulus of the difference. This is just numbers, right? This is bounded by, which means it's less than or equal to twice this error function. Okay. So this is the operational statement of what it means to approximate these two unitaries, right? So when I say that any single qubit unitary can be approximated by this set, which is H, S, and T, it can be approximated to arbitrary accuracy, which means I can make this error function as small as I want, right? So the statement of universality will then be that any single qubit unitary, which is any U which is a 2 cross 2 unitary which belongs to SU2, can be implemented using H, S, and T to arbitrary accuracy in E, U, comma V. So this is the metric or the measure that we will use to judge how accurate decomposition is. Of course, the exact statement will quantify this precisely. So if you want to implement your gate U with a certain accuracy E, then you will need a certain number of Hadamard S and T gates. So obviously, the larger and larger the circuits you have for a single, I'm talking about implementing a single SU2, right? The more gates you add to that decomposition, the closer you will get in accuracy. So there will be a kind of trade-off or a scaling, right, between how many gates you need to implement a given arbitrary unitary and to what accuracy you can implement it. Okay, so this sort of pretty much what I wanted to say about universality and approximating unitaries, exact universality, etc. I hope these ideas are clear. I will have a couple of problems based on this in the assignment, which should clarify some of these things better, right? But I don't want to get into more detailed arguments about, there is a whole, there's a lot of nice math and algebra around here. So I want to just mention one thing though, that this last statement can be made more precise by what is called this Solovay-Kitaev theorem, okay? And of course, this is the reference would be chapter 3 of Nelson Chuang, right? No, I want to say chapter 4, right? So they give a very nice description of this statement, right? And also, of course, they give a proof, which is what I'm not giving, but I encourage you to go read up on this. Okay. All right. So, questions?
Excuse me, ma'am.
Yeah.
When we were discussing the exact part of this universality argument,
Yeah.
in 1B part, you were exactly decomposing a two-level unitary into single level as a product of single level unitaries, right? Not single level, single qubit unitaries.
Yes.
Just wanted to confirm that.
Was that your question?
No, I just wanted to confirm that it was single qubit gates, right?
Yeah. See, a two-level unitary can be in any dimension. Like here, it's in 8 dimension, right? The point is that such a thing does not really need an 8-dimensional gate. It does not need a full 3-qubit gate. It needs a single qubit gate and a bunch of controls. Okay, that's the statement. Okay, so let's now, the last, I don't know, we have maybe another 2 to 3 weeks of lectures. And in this time, I would like to now focus on quantum algorithms, right? And there are 2 kinds of algorithms that we can talk about. So with all the machinery that we have now, let's look at what can all these quantum gates and circuits really do, right? So I would say that there is 2 broad classes of algorithms, right? At least these are the only 2 that we will look at for the rest of this course, right? One is the so-called oracle-based algorithms, right? And the other is what I would call the quantum Fourier transform based algorithms, right? So there are 2 fundamental techniques, right? One is this idea of designing an oracle for a particular problem, designing a quantum oracle, and then using that to show speed up, or using that to get a speed up. The other approach is to use a quantum Fourier transform. So one of our tasks in the rest of this course will be to show that the quantum Fourier transform is actually exponentially faster than, say, a discrete classical Fourier transform. Okay. So there is an exponential speed up. So even if you compare it to something like an FFT, like a fast Fourier transform, you can show that the quantum Fourier transform can be done exponentially faster. So in other words, the scaling or the resources that are required will scale polynomially in the number of qubits rather than exponentially in the number of qubits. So that is what we call an exponential speed up, right? And the second category of algorithms are those which, like I said, use the oracle-based schemes. So we've already seen one of these, right? Have we already seen a quantum oracle?
Deutsch's algorithm.
Deutsch algorithm.
Exactly. So we already saw an example of this with the Deutsch. So I'm quickly going to recall today what the Deutsch does. And then tomorrow we will look at the full-blown version of this, which is the so-called Deutsch-Josa algorithm, right? And the third and most important algorithm actually which comes in this class is what is called the Grover search algorithm. Okay. So this also is based on constructing a certain quantum oracle for the search problem. So it's useful, therefore, to start with Deutsch, look at Deutsch-Josa, which is just an extension for an n-qubit system instead of a single qubit system, and then study the Grover search. So this is what we'll be doing for the next few weeks. Now, interestingly, while it turns out that in the case of Deutsch and Deutsch-Jozsa, once again, you have an exponential speed up. In the case of Grover's search, you have a quadratic speed up. Okay. So I also want to then briefly talk about what one means by exponential versus polynomial, etc. So the question is the following. So when you have any problem, so let me just say a few loose words on computational hardness. Okay. So the question is, given any problem, right? Let's say that I have a certain problem, by which I mean a computational problem, which is defined on n qubits. For example, it could be defined on some natural number n, right, which is close to 2 to the n, right? So that's when, for example, you can think of searching over a database with capital N entries, right? Now this capital N, you could say, is smaller than or equal to, or the closest integer to, the closest power of 2 that you have to this is a 2 to the n, right? So we'll say that this is approximately 2 to the n, or you have a ceiling function which is 2 to the n. Then how does the circuit size scale with n, right? So what is roughly the number of gates, right? How does that scale with n? So you could either talk about circuit size, and when you talk about circuit size, you could talk about the depth of the circuit, or you could talk about the breadth of the circuit, right? Or you can talk about what is called gate complexity, which is how many gates do you need? How does that scale with n? Of course, these two will be related, but it's easier often to just get a handle on gate complexity, right? And scale with n means how does it grow with n, right? And if this grows as a polynomial function of n, so if the number of gates goes as poly n, we say that it's a, so we need a circuit of polynomial size, essentially, right? And in the classical computing language, this is what will constitute the class, computational complexity class P, right? In the quantum case, we don't really have the class P. What we have is something called BQP, right? Which means this is bounded quantum polynomial. Okay, and we say bounded here because in the quantum case, these are not truly deterministic. I mean, you may not always have deterministic algorithms, you will rather have probabilistic algorithms. So we'll find this to be the case. For example, when we do Grover search, you'll find that you get the search, you get the correct state that you're searching for with a certain probability, right? Similarly, when you do the quantum Fourier transform, of course, I forgot to mention that the quantum Fourier transform leads to the famous factoring algorithm, the quantum factoring algorithm. So that will be the sort of concluding piece of this course, right? So this, again, you will say that you can find the factors, the prime factors, with a certain probability, right? So these are probabilistic complexity classes, right? So this is what is called a probabilistic which is different from the classical classification where you have P and NP, right? Which are roughly what you can solve in polynomial time or polynomial size, and what you cannot solve in polynomial time or polynomial size, but what you can verify in polynomial time or polynomial size, right? So roughly this is how we will classify this now. So we'll say that if this gate complexity grows as a polynomial function of n, right, then you're within BQP. And both the search and examples of this will be the search and factoring. So both of these in the quantum case are in the class of BQP, right? On the other hand, if of course the gate complexity were to grow exponentially, right, then this would be a problem that is considered hard even in the quantum case, right? It's not just hard classically, but it's also quantum hard, right? And the associated class, so the analog of what would be called NP in the classical case is something called QMA. Again, too much detail, which I will not get into, but I will just put in brackets what the classical corresponding classes are. We cannot exactly have the same classification here, like I said, because these are probabilistic algorithms, right? So there are these so-called randomized algorithms in the classical case, right? So we have to really compare with randomized classical algorithms. And in the quantum computing literature, we've evolved our own sort of complexity classification, which are called BQP and QMA. Okay. So this is more by way of general knowledge that I'm telling you these things. I will not have time to dwell on this in detail, right? Okay, so I don't know, should I stop here and start Deutsch tomorrow itself rather than get into it now? It may be a bit tricky to do this now, right? So it turns out that Deutsch and Deutsch-Jose are basically kind of toy problems, right? Where you do see an exponential speed up. Actually, this gates size, so maybe I'll conclude by talking about this instead. Okay, so I said that there are two ways of doing algorithms, right? There is one which is these Oracle-based algorithms, and the other which are the Fourier transform-based algorithms. And factoring is a Fourier transform-based algorithm. The Oracle-based algorithms, you don't really talk in terms of gate complexity. Okay, so when I say computational hardness, I should mention separately that in the case of Oracle-based algorithms, the notion of hardness comes from what is called Oracle complex. Query complexity. Yeah, the technical word for this is what is called query complexity. Okay, and now the complexity is basically number of queries that you need to make to the Oracle. And the question is whether this goes as a polynomial function in n, or whether this goes as an exponential function in n. Okay, so yeah, I'm sorry, I should have mentioned this right there, that you have the notion of gate complexity, and then you have the notion of query complexity. So the Deutsch and the Deutsch-Jose, so let me generally say Deutsch-Jose, right, is polynomial in terms of Oracle complexity or query complexity, right? You do not really worry about the circuit complexity of implementing the Oracle itself. And this is something I think I mentioned even at the very beginning when I discussed the Deutsch algorithm, that what you really care about is how many times do I need to query the Oracle. In fact, it's not even poly, it's actually fixed, it is fixed in query complexity, which means actually you need exactly one query to the Oracle. So this is often called a constant, query complexity. So Deutsch-Jose does even better than poly, right? It's just constant. No matter how many, how big you make your input size, the number of queries you need is exactly one. Whereas classically, of course, we'll argue that the queries actually grow exponentially in n, right? So when you compare Oracle-based algorithms, you have to look at the query complexity, which is how many queries you need to make to the Oracle. Even in the case of search, that is what we will do. We will say how many time steps, right? How many times do you need to run the Oracle? Or again, how many times you need to query the Oracle in order to hit an element of your search, right? In order to hit a state which is the output of your search, right? And again, you will find that that scales, quadratically, whereas the classical, I mean, that is quadratically faster than the corresponding classical search algorithm. Okay, so let me stop here because I think it's not useful to start discussing Deutsch and Deutsch. So it's best to do them together tomorrow. Okay. Any questions?
No, ma'am.
Okay, so if not, we will meet tomorrow. Okay, so I'll see you all tomorrow at 9.